Now I would like to compute a triple integral. I will show you an example where I will calculate the volume of a sphere by using a triple integral. That's just basic math. The formula for the volume of a sphere is very well known, but I think it can be useful to show this example because we will adopt a different frame of coordinates in which we will use spherical coordinates. And that's very important when we have some types of symmetries which can be related to spherical geometry. We need to consider three axes in this case, and we need to know how to shift from this set of coordinates to the so-called spherical coordinates. We have a point P, which has a certain distance from the origin, and this distance is r. The projection of P on the xy plane describes this other vector, which spans an angle theta from the x-axis, and this theta is another parameter. We have r, we have theta, and this theta is just the same as in the case of polar coordinates that we saw, but we need another angle, and this angle is the angle that r spans starting from the z-axis, and r ranges from 0 to infinity, whereas theta ranges from 0 to 2 pi, as we saw when we talked about polar coordinates. Phi doesn't range from 0 to 2 pi, it starts from 0. In order for this set of coordinates to be consistent and to not describe the same points with more parameters, it's just enough that phi ranges from 0 to pi, if you think about it. To describe all points in 3 dimensions in spherical coordinates, these ranges are just enough. Another thing that we need is to describe the parameters x, y, and z, the coordinates x, y, z, in terms of r, theta, and phi, because we need to calculate a Jacobian of the transformation from x, y, z to r, theta, and phi. Well, this is not difficult because x is the coordinate of the point P. What is the coordinate of the point P? Well, we need to calculate this projection here, which is r times sine phi, because phi is also this angle right here. R sine phi is this projection, and then we need to multiply by cosine of theta if we want x. So it's r sine phi cos theta, whereas y is just r sine phi sine theta, because it's this other projection, this other coordinate, which is the same as this one, if this is a rectangle. And so it's r sine phi sine theta, whereas z is just r, this is much easier, it's r cosine phi, this is just z. This is our set of coordinates. So if we want to calculate the volume of a sphere, we need to compute a triple integral of dx, dy, dz. So this is a volume, right? If I multiply by a function f of x, y, z, that would be an hypervolume. It doesn't have a geometric interpretation. When we shift from this domain, which I can call D, this is the domain which represents the integration over a sphere. Then we will have a triple integral in another domain, which is the domain of the spherical coordinates, and we have the Jacobian of the transformation, which is del x, y, z, and then we have del r theta phi. The order of the coordinates doesn't matter, because you get the same thing. This is the determinant of the Jacobian matrix, which is the Jacobian. So when I say Jacobian, it's already the determinant. And then multiply by dr, d theta, d phi. So we need to calculate this Jacobian. Remember that we also consider the absolute value, because we are talking about areas, or in this case volumes. And then we will have the domain d prime. And anyway, let's compute the Jacobian. We need to compute the absolute value of the determinant of dx over dr, dx over d theta, dx over d phi, dy over dr, dy over d theta, dy over d phi, dz over dr, dz over d theta, dz over d phi. So let's do this computation. Dx over dr is just sine phi cosine theta, and then we have dx over d theta, which is minus r sine phi sine theta, and then we have dx over d phi. Dx over d phi is r cosine phi cosine theta, and then we have dy over dr, which is sine phi sine theta. Dy over d theta is r sine phi cosine theta. Dy over d phi is r cosine phi sine theta. And then we have dz over dr, which is cosine phi. We have dz over d theta, which is 0. And then we have dz over d phi, which is minus r sine phi. We have to compute this determinant. Let's brace ourselves. This will be a little boring, but the computation needs to be done, so let's do it. We can expand the determinant in terms of the last row, in this case, because it's easier. For instance, take the first term here, which is cosine phi, and then cover the last row and the first column and compute the determinant of this submatrix. So it's minus r squared sine phi cosine phi sine squared theta. So it's minus r squared sine phi cosine phi sine squared theta minus r squared cosine phi sine phi cosine squared theta. And if you take a look here, there are common factors, this one and this one. It's like minus r squared sine phi cos phi times sine squared plus cosine squared theta. So that's 1. So let me just rewrite the expression, which is this one, minus r squared sine phi cosine phi. And then we have 0 times the determinant of this submatrix, characterized by this element as the 1, 1 element. Then we have this one, the 1, 2 element. This is the element 2, 1, and this is the element 2, 2. Because we just need to cover the second row and the last column to compute the determinant of the submatrix. So we have plus 0, and then we have minus r sine phi times the determinant of this matrix, which is r sine phi squared cosine squared, r sine phi squared sine squared phi cosine squared theta, plus r sine phi squared sine theta squared. In this expression, you see the common factor is r sine squared phi, and then we have cosine squared plus sine squared. This is just r sine squared phi, and this becomes equal to minus r squared cosine squared phi sine phi minus r squared, because there's r here, minus r squared sine squared phi times sine phi. And then we have a common factor here, which is r squared sine phi, as you can see. R squared sine phi, and then we have cosine squared plus sine squared phi. So that's 1. This becomes equal to minus r squared sine phi. But remember that we need an absolute value when we calculate the determinant. So this minus should be replaced by a plus when we put it inside the integration, because r squared is positive, sine phi is also positive because phi ranges from 0 to pi. The sine is positive when the angle ranges from 0 to pi. All in all, the integration that we need to carry out is this one, triple integration of the Jacobian, which is r squared sine phi times dr d theta d phi, where r ranges from 0 to r, which is the radius of our sphere, theta ranges from 0 to 2 pi, and phi ranges from 0 to pi, as I said, to describe the sphere. As you can see, this function is constant with respect to theta, so when we evaluate the integration between 0 and 2 pi, we get 2 pi. So we can write it as 2 pi integral 0 pi integral 0 r squared sine phi dr d phi. The integrals are independent of each other because you see there is one variable which only depends on phi and one which only depends on r. We can rewrite it as the multiplication between two independent integrals. So it's integral 0 to pi of sine phi d phi, and then we have integration from 0 to r of r squared dr. These are very simple integrals because this one gives us minus cosine of phi, and then evaluate it between 0 and pi, and this is equal to 2. And then we get a factor of r cubed over 3, and then compute it between 0 and r. This is r cubed over 3. So all in all, we get just 2 pi times 2 times r cubed over 3, which becomes equal to 4 pi over 3 r cubed. So this is the result, and this is something that we already know from basic mathematics.